welcome back. So, when someone is implementing a module, it has in his mind a well-delimited set of features that are offered by his module. Now, when he wants to publish this module, to have the module used by other programmers, he wants these features to be described in something like a user manual, so that they are used in the way they are designed to. What does that mean exactly? Well, functions preconditions must be verified by the client. Also, the client should not break data invariants that are in the key for data structure to work. Also, the client should not use definitions that is internal, that should be private, because it may change in the future. So that's like a contract that must be respected in exchange for the module features. Moreover, the type checker will help us to enforce the data invariant of the data structures, and also will prevent the client from using definitions he shouldn't use. So the syntax to assign a signature to a module is the following one. You use the keyword module, M, like in a standard module definition, colon, and just after the colon, you write the signature you want to assign to this module. In fact, you can name a signature so that you don't have to rewrite it if you have to write it several times. To do so, you use the keyword module type followed by the identifier of the signature, and then you just write the definition of this signature. Again, an identifier of a signature must start with an uppercase letter. Then, of course, you can use these names to constrain some module implementation. So let us now define a module for natural numbers. A natural number is a positive integer. So we will use the type int to represent a value of natural number. We will have only three functions, three values. The first value is 0, that represents the 0 natural number. And then you have the ability to go from a natural number to the successor of this natural number, and also from a natural number to its successor. The implementation is straightforward, except that you have to take care not to break the invariant that the int that you are using to represent a natural number is indeed a natural number. So here you have to take care not to overflow, which means incorrectly, which means that when you take the successor of something that is max int, you don't want to do +1, otherwise you will go to min int. You prefer to return 0 in that case, and if n is not mixed int, it is then between 0 and max int -1, so you can do n+1. The same kind of reasoning is applied to pred, saying that you don't want to take the predecessor of 0, and that time we choose to stay at 0. So this valid module can be given to the OCaml top level, and indeed it is accepted. And we can try to use it. For instance, here I define the function which performs the addition between two natural numbers, x and y. If you have the fact that x is equal to 0, you return y, because 0 plus y is equal to y, and otherwise you call yourself recursively by computing x minus 1 plus y. And finally, you take the successor of this natural number to get the result of the addition. So this is working well. The problem is that it is also easy for a client to break the abstraction. Here, for instance, as I know that t is equal to int, as a client, I can use the module in a bad way by providing -1 to the function pred, and I get a natural numbers which is negative, and this is very wrong because it is against our invariant. So we have a problem in this example because some invariant is broken by the programmer that used a fact that he shouldn't use. The fact that t is in fact implemented by integers. Well, we could write a comment in the signature saying that it should be gentle and don't use this fact. But still, the temptation can be very hard to resist. That's why we will use what is called abstract types. That will give no choice to the client programmer, but to respect this rule. So let us come back to our example. And let us change just a small thing in the interface. So in the signature, I will remove the equality between t and int. So now, in the signature, we just know that there exists some type t, but we know nothing about its implementation. So let us check that the top level accepts this definition, and indeed, inside the inferred signature, we can see that type t is just declared, but no implementation about type t is given. So type t is a type identifier that is just equal to itself. But if I try to apply this pred function to now an integer, I can't, because for the type checker, naturals.t is a type that is different from int. So what we have done with an abstract types is just to hide the definition of the type. So now the signature does not publish t's implementation details anymore, and the type checker ensures that the clients cannot use that fact. So that's exactly why t is called an abstract type.